Welcome back to ECE 320A. You should be finishing your reading of chapter number 10 and starting to complete homework number 2. We're getting close to the end of unit 2, and you can find practice material for exam number 1 in the module referred to or labeled exam number 1 review material in D2L. What I want to do now is work through an example illustrating power factor correction. And we've actually seen in an earlier example where if we had two loads, those two loads could actually locally be pushing or sharing or exchanging current back and forth and not requiring the source to actually be supplying as large of a current magnitude as we might need to support each of those individual loads. Well, now we're trying to generalize that and talk about how can we introduce another sort of load element, which is this highlighted capacitor in this illustration or in this circuit. In the box is the collection of all of our loads independent of the introduced capacitor. But what we want to do is we're assuming that all of the loads in the black box have a power factor that's less than 1, and we're assuming that it's an inductive load so that we now have a current that's lagging in that portion of the system, and we want to now not demand as much current from the power company, or we want to reduce I sub S bar by introducing a load in the form of a capacitor or a capacitor bank that will try to be selected to move the power factor of the combination of the load and this capacitor. Now this is sort of our overall load. We want that power factor to be closer to 1, which means that we now are not being as demanding on the source if we can make that happen. And in this example, we will probably just go ahead and find a capacitor value that will set the power factor of the combination of those loads and the capacitor equal to 1, but it may be that you want to adjust that to something that's not quite equal to 1, just so that you understand how this process works or how to go about doing this. Here's the example that we are going to use for illustrating the power factor correction technique. We have two loads, and you've already looked at load number 1 in quiz 2.2, I believe. But in an earlier quiz, you've now tried to find the complex power of load 1 given the information that's included in this box. We also have load number 2, so we have the net effect or the combination of these two. And now what we want to do is introduce a capacitor, an impedance element, in parallel with those two loads so that we can correct the power factor or move the power factor closer to a value of 1. Now note here we have one load that's lagging and one that's leading, but the overall effect might be that the net of those two in combination might be lagging, and that's why we're now introducing a reactive piece that produces leading current nature, and so we want to have I sub G lowered by introducing this capacitor. Again, the supply is going to have 500 volts and that's in RMS, and it's at 60 hertz. And let's now just get ready to analyze this or talk about how we actually find this capacitor value when we know omega. Omega is 2 pi times 60, and the only unknown really, well, there's a couple of unknowns. One is, what do we want our ultimate power factor value to be? In this case, we'll probably let it equal 1. But once we've selected that, then how do we back out or evaluate or find the capacitor value C? As I said, in your quiz, you've already found this complex power for load number 1. So let me just quickly go through that. You were given the average power or the real power and the power factor. From that, you can compute the apparent power of load 1. That's 48,000 divided by 0.6. Now you have two sides of the right triangle. You don't have the vertical side or the reactive side, but you can solve for that because you now have the angle theta 1. You have, that's from the power factor. You have the apparent power, which is the hypotenuse, and you have the real power, which is the horizontal piece. And because we were told that the power factor was lagging, we know that the reactive component is positive, or it's going up in the vertical direction. So we've now found the complex power of load 1, or you've already found that. It's 48 plus J 64 kVA. We can do similar analysis to find the complex power of load number 2. We were given the average power of 24,000 watts, a power factor of 0.96. The distinction now is we were told that that particular power factor was leading, which says that we now have a capacitive type load for load number 2, and that then we identify by assigning a negative sign for our reactive power, or now we're going down for Q sub 2 in relative to the horizontal length of 24,000. Now we go down in the vertical direction, 7,000 volt amperes reactive for a complex power of load 2 equal to 24 minus J7. Now that we have those and we know the way that we can combine complex powers, we just add up their component parts. We can now find the total load power due to those two loads. Let me go ahead and call that total complex power of load 1 and 2 as S sub 1, 2 bar, and that's just going to be the real power and the reactive power, where P sub 1, 2 is going to be the real power of the two loads added together, and that ends up being 72 kilowatts. That's our real power, or the average power. Our reactive power of those two loads is now the combination, and we have to make sure that we obey the signs. This isn't the absolute values. We have to get the algebraic sign. So we now have the reactive power of load 1, which was 64, and we take away from that, or subtract from that, 7 from load number 2 to end up with a reactive power of 57,000 volt amperes reactive. And we can see that that particular result was positive, which says that we now have a lagging current in the combination of loads 1 and 2, which means that net we have an inductive type load. From P12 and Q12 we have now the complex power, but we can also find the absolute value of that to find the apparent power of those two loads combined, and that's now just going to be the hypotenuse of this right triangle formed from the real power, or the horizontal power, and the reactive power, Q sub 1, 2. If we do that, we now have 72,000 squared plus 57,000 squared. Take the square root of that, and we end up with 91.8 kVA, and that's our apparent power for this particular system. We could also compute the angle of that combination of loads 1 and load 2 by doing the inverse tangent of the reactive part, which was positive, of 57, and a horizontal part of 72. I don't need to worry about the thousands. Those have now canceled out. The numerator is a little less than the denominator, so we know this angle better be a little bit less than 45 degrees, and it ends up being 38.37 degrees, and it's positive, and that then says that we have a power factor for load 1, 2, or of the combination of the cosine of that 38.37 degrees, and that gives us then a 0.784 lagging. And before we try to move that closer to 1 by introducing a capacitor, let's just look at the load currents and how those, or what they are, and then we'll find how that will then relate to the corrected current that's being asked or demanded from the supply or the source. So to find the load currents, we can use our generic formula for complex power, which says that complex power is the voltage phasor times the complex conjugate of the current phasor. That's a complex quantity, but we know that we can take the magnitude of both sides and the relationship is still valid. Or we can now find, using the apparent power, it's just the product of the magnitude of the voltage and the current. These two loads were both in parallel and they shared a common voltage of 500. What we now can use are the complex power magnitudes of both of those to find the magnitude of each individual current at the load. Or we can say that the magnitude of the current going through load number 1, so if we now go back to this diagram, there is I1 bar. We want to know what's that magnitude, and here is I2 bar, and what's the magnitude of that current. The magnitude of I1 is now going to be from this apparent power formula that we found from the complex power equation. We now have the apparent power of load 1 divided by the magnitude of the voltage that's supplying that. We found the apparent power of load 1 to be 80,000. The voltage supplying that was 500, where we now have 160 amps for load number 1. Load number 2 is now going to be found similarly. The voltage is the same because we're in parallel, and the apparent power was 25K. This ends up being then 50 amps for load number 2. And we can actually now find the magnitude of the total load current. Because of the information that we now possess, or the data that we now have. And what we can say now is we have the apparent power of the combination of loads 1 and 2. That's now this square root of P12 squared plus Q12 squared, which we found to be 91.8 kVA, and I sub 1, 2, the current magnitude, is now going to be the magnitude of the apparent power, or the value of the apparent power, divided by the voltage, which is now 91.8 K divided by 500, which is 148 amps. And before we move too much further along, let's go ahead and just look at what we have when we compare these currents. Hopefully you can now see that, in fact, the magnitude of the current that supplies load 1 and 2, which is 184, is not equal to the magnitude of the current for load 2 plus the magnitude of the current for load 1. There's 210 on the right and 184 on the left, and this just emphasizes this point that I've tried to make earlier, that currents and voltages are phasors, and we have to worry about magnitudes and angles and not just magnitudes. And what we want to do now is we actually want to try to improve the power factor and see if we can reduce that 184 down by introducing a capacitor into the load side or near the load, so that we can maybe reduce the demand of the generator side or on the supply side of our circuit. So what we want to do is we now want to correct the power factor, and we're wanting to do that by adjustment or introducing a capacitor. And I might just say that here we want to move the power factor total equal to 1. We want it maybe equal or closer to a value of 1. So let's see how we can do that. We want to be green. We want to now reduce the magnitude of the source current, and that means that we're reducing the apparent power, because the apparent power, we're supplying 500 volts. If we reduce the magnitude of the source current, then the product of that voltage and current will obviously be smaller, which now says that we're reducing the power demands on the supplier or from the generator side, and that's now more efficient, and that's why I'm saying we're shooting for a green result in terms of our ultimate goal. And here's the picture, or pictures. I'll have one after this. We have load number 1, and we have load number 2. And we've already computed those complex powers. What we want to do now is introduce a capacitor as another basically component on the load side of our diagram, such that that capacitor will help supply current to this more inductive load. Here is just another circuit diagram that's consistent with the one above. We've now just collected the two loads into one, and now what we have is S12 for the complex power of load 1 and load 2 in combination is 72 plus J57, we want to now introduce another impedance near the load to try to drive the power factor right now that's due to just this particular load to a value of power factor that's closer to 1. And here's the picture. If we look at the apparent power of the combination of loads 1 and 2, then that gives us a hypotenuse of 92,000. The real part is 72,000 and the reactive part is 57. What we want to do is introduce this capacitor to provide us with negative reactive power, and that's going to allow us, and hopefully you can see that we could pick a capacitor that would put us down here with Q sub C. It could put us down here. If we put it down to be exactly the negative of Q12, then we will be right at that point with respect to our apparent power will be equal to our real power, and we'll have a power factor of 1. So what we're trying to do is we're trying to now select Q sub C, and in some cases you may be able to introduce more capacitance than in others, but in our case we're assuming that we have the ability to introduce whatever capacitor value we need, and in that case we will want Q sub C to exactly balance Q12 so that we can have our apparent power equaling our real power. And that will then really allow us to reduce the demand on the source and reduce the current that is being requested from those two loads, loads 1 and 2. They haven't changed at all. And they're still able to receive what they need, but now that capacitor is providing this exchange of power closer to the loads and allowing the supply to not have to be as large as in the past. So now let's find out what we need to request from Z sub C, the impedance of this capacitor that we are adding, in order to make the reactive power from that impedance, Q sub C, actually cancel the reactive power in loads 1 and 2. And for that, what we can do is just start going back to what we know. And that is, what's the impedance of a capacitor? This you should know until you retire. This is now 1 over j omega c. That's in sinusoidal steady state, which says then that what's the complex power associated with that particular impedance? Well, the complex power hasn't changed in terms of its formula. That's the voltage phasor times the complex conjugate of the current phasor. What do we know? Well, we actually we're demanding 500 volts for the loads, and so we know V sub C. We can write this now in terms of our voltage formulas for voltage and impedance to give us our complex power. Or in other words, let's get rid of or rewrite the current of our capacitor in terms of voltage, which is now V sub C. This is the generalization of Ohm's law, and we now need to conjugate that so that we now have V sub C conjugate in the numerator, and dividing that we have Z sub C star, or the complex conjugate of our capacitor's voltage, or I'm sorry, of our capacitor's impedance. And we know what the impedance of the capacitor is. That's 1 over j omega c. That means that Z sub C conjugate is just the negative of that, and we could put the negative sign wherever we want. I'm going to put it downstairs so that now we can say that we have the following. Z sub c can be used in our complex power formula, and we now have V sub c squared over 1 over minus j omega c. That's just V sub c magnitude squared over the complex conjugate of our capacitor's impedance. But now that denominator and the denominator jumps upstairs, and we now have then a formula for the complex or the reactive power, actually the complex power of our capacitor, which we're assuming an ideal capacitor which doesn't have any resistance to it. And we now have minus j omega c times the magnitude of our capacitor's voltage squared. And in this particular case, omega is 2 pi f, and we're in the United States, so our frequency is 60 hertz. We now have 377 for omega, radians per second. And what do we want the complex power of our capacitor to be? Well, that's now what I was saying up here. We can make it whatever we want, but if we have total control over that capacitor, we could make Q sub c be exactly the opposite in sign of Q sub 1, 2, so that we exactly cancel the reactive power in the overall circuit of the capacitor and loads 1 and loads 2. So let's do that. Let's just say that we want the complex power of our capacitor to actually be minus J 57, and that's 1,000. So that we exactly cancel the reactive power, net reactive power from loads 1 and loads 2. And this we now can set equal to our formula, which was minus j omega c V sub c squared. Or in other, now solving for c, that allows us now to, the minus j's cancel. We have 57,000, and we divide that by omega and the magnitude of our voltage squared. So we now have 57,000 divided by omega, which is 377, and our voltage was 500. We square that, and we end up then with a capacitance of 605 times 10 to the minus 6 farads, or 605 microfarads. So let's see what we've now produced. We can now look at the load power of load 1, load 2, and the capacitor. So let's just say the load power with the capacitor. Or this is now after the power factor correction. We selected the capacitor to exactly cancel the reactive power, the net reactive power from loads 1 and load 2. So now we have the total complex power of the loads. We now effectively have 3 of those. We have the complex power of loads 1 and 2, which we've already combined into one expression S sub 1, 2, and we now have introduced a capacitor to try to help us make the system a little bit more green. So in this case, we now have '72 plus J57, that's S12. Then our capacitor was minus J57, and all of these are thousands, so we have kVA. So that now the load associated with the capacitor, load 1 and load 2, is now purely real. The complex power is now all real. And we can now use that to say, okay, if this is now what the load is requesting in aggregate, what's the source having to supply? Or what is the new current magnitude supplied by the source? Well, now we can use our complex power formula again. We know that we have the total complex power. We know what the source voltage is. We can now use that to find the current now being requested of the source. And we can do this all in terms of magnitudes. So that now we can say the magnitude of our source current is now equal to the apparent power of all of the loads divided by the magnitude of our supply voltage. Or this is now 72,000 divided by 500, or this is now 144 amps RMS. And do you remember what we had before we introduced the capacitor? Where the capacitor was our power factor correcting capacitor, our generator was having to give us a magnitude of current of 184 RMS. And we've just now computed that with the power factor correction, I source is actually 144, which is a lot less than 184. And we can actually see that this is giving us something that was consistent with what we had in an earlier example. So now the source, we're requesting less current from the source, but we can also see that the source current magnitude of 144. So this is the power factor corrected source. That's actually less than 160 amps, which was the current that was required by load number 1. This is now and it hasn't changed. Load number 1, we didn't change load number 1 at all. And in fact, the source now is giving us less current than what load number 1 demands. So what's going on? Well, in fact, loads number 1 and loads number 2 and the introduced capacitor are exchanging stored energy via these reactive currents. So at the load side, where we've now introduced that capacitor, when the inductive load says, I need more current, the capacitor now shares its current with it at the local side of the load. Or another way of thinking of it is that these reactive currents circulate between the loads and the capacitor near the loads, and because they are able to locally near the loads exchange these reactive currents that the true loads are requiring, we don't ask as much for the source. So now a company might be in better shape if they actually build in some capacitive banks when their circuitry or their loads are heavily inductive. They may get charged less from the power company since the power company is having to produce a smaller power to deliver to that particular load. And that then says that this current that's required of the source is less, and so it's not losing as much through the transmission lines that are feeding that particular load side of load number 1, load number 2, and that compensating capacitor load provided by the capacitor. So that's how this concept of power factor correction works, and hopefully now you can understand how to manipulate your capacitor's value in order to produce the amount of reactive power that you want to produce the power factor at the load that you need or are demanding.